Hello everyone, welcome back to our YouTube channel Becoming a ROS Developer. I'm Desire and today we've got Khai, who has just completed the course Linux Basics for Robotics, and he'll be giving us a presentation of that. So let me now hand over the platform to him so he can begin his presentation. Alright Khai, whenever you're ready.
Hi everyone, my name is Khai. Today I will be presenting the Linux Basic Real Robot project. So now I will try to connect with the real robot.
I think you're already connected, Khai.
Hello?
Yes, you're already connected because you can see the robot in your on the cameras there, so it means you're already connected.
Yeah, I will try to run the coding. So we can see the virtual robot in the RVIZ software. So now I will run the obstacle avoidance command. So first it will initialize the robot to make the connection and reset all the parameters.
Okay.
So it will say robot initialize, and then this will make the robot to stop initially before it run everything. So the real robot starting to move. And you can try to see the output. So first it will detect the range from front left, front right, left and right. And then you will see whether the front is free or not. So for this case, the front is free. So if you're moving forward, is fulfill the third condition in the script.
Okay.
So it will move 0.272 meters and 1.22 seconds. So every time after it moves, it will reset back to the linear velocity will reset back to 0 to prevent the real robot crashing or having problem. So just now you can see the front is free and the front right is also free, but we still make it moving forward because the original coding is like moving right, but I think our task is to move around the path, so that's why I make it moving forward again. So now it's also moving forward. I actually let the linear velocity very slow because in simulation it's okay to set the velocity very high, but I found that in real world the delay to control the real robot is too much. So that's why I need to set the velocity very low so that I can counter back the delay that sending the command to the real robot.
Okay.
So we will try to see when we try to rotate, it's almost there. So now you can see the front left is 0, the front is also not free, front right is also not free, so that's why you will find the left and right range, checking which has the better free path to move at. So it will define the right have greater range, so that's why it's turning right by 90 degrees. And then you will again rotate by 90 degrees to the right. So yes, as you can see, the real robot is moving right to the free path. So now you can see the front left is 0, front 3 is also 0, but the front right is 1. So this means we cannot move forward, so that's why we turn slightly right by 45 degrees. I think the real robot crashing the wall, so that's why disconnect to the real robot.
Okay, try disconnecting and then reconnecting again and let's see. It doesn't look like it's responding. So.
Yeah, it's quite slow in my laptop, so that's why I need to wait a bit longer.
Okay.
Yeah, now it will turn right by 45 degrees.
Mm-hmm.
So as you can see, there are more free paths to add. So I think now you will just move forward. Yeah, he will moving forward.
Okay.
So overall, you can see the movement in the software. So I can now run another script to show the statistic.
Mm-hmm.
So I will open another terminal. So basically, this script will display the distance range, direction of the robot, the optometry position in XYZ,
Mm-hmm.
and orientation in RPY, and the IMU angular velocity XYZ, and the linear acceleration in XYZ. So now actually we will show like this, the expression as shown here. So the current distance range is 2000 meters. Now it's 2007.
Is that meters?
Yeah, meters.
Okay, how did we get to that?
You mean how to get the distance range?
Yes.
Actually, I'm using the get autometry distance. So as shown here, and this value I think is getting from this software, because here we got the autometry features here. I think it's getting from this software.
Okay, so I want you to do one thing for me. So go back to the script where you were copying your commands from, right? So the one you're running in the terminal, right? So
this way.
Yeah, now I want to look at the first two. So the ones that appear just after the shebang line, right? Can you explain to me what each one of those two are doing?
You mean these two?
Yes. So start by that one. What is it doing? When you execute that, what does it do?
So first, the source command is actually let the Linux has a permission to run the patch file, because normally the patch file is like blocking. So that's why we need to use a source command at the front to give a permission to the Linux to run this file, the bash script file. And then the second command is a ROS2 launch. ROS2 is a robot operating system. This will run the Turtlebot Gazebo script file, and the title name is the Turtlebot 3 Gazebo is the title name, and then this is the file that associate with the Turtlebot 3 Gazebo.
Yeah.
So these two will run the.
Okay,
these
so
two will run the software.
So okay, if you are connected to the real robot, right? Do you need those two? Do you need, based on your understanding, do you need to run those two?
Yeah, based on my understanding, these two are the first step to run the real robot. We need to execute these two commands before we running to the real robot.
Why do we need to do that? Because the reason why I'm asking. Go ahead.
Now we may need to like visualize the path of the robot in this software.
Yes, but remember, when you run those two, you're not visualizing based on the real data. That's why I'm asking, why do you think that it's relevant to run those? Is it something that you're just following, or what's going on there?
Yeah, I'm still the beginner, so I'm following the guideline to say that before running the real robot, we must execute these two commands first.
Okay, all right. Yeah, because it's important for you to get to know why you're doing those things, because it will aid in your understanding, right? If you don't really understand it, research it, find out, why do I need to run this prior to running the real robot, right? It will help you understand better. Okay.
Yeah.
All right. So let's go on.
So the real robot origin reaching here. So now it will turning right by 90 degrees. So I think that's all for the real robot demonstration. Maybe we can move to the simulation
Yeah,
in
okay.
the gazebo.
Yes, let's see it in simulation now.
So I will maybe not need to. I need to disconnect first.
Yes, you need to disconnect it.
So the same thing, before we running any simulation or connecting to the real robot, we
Mm-hmm.
need to execute these two commands.
Mm-hmm.
So I just copy here to simplify the process. So it will actually automatically open the gazebo window here. So inside there, I need to run the second command for me to interface with the virtual robot.
Mm-hmm.
So in the second terminal, I will again run this command. So after 5 seconds, you will connect to the virtual robot. So it says ready, so I can now interface with the real robot. So now I will run the obstacle avoider batch path in the third terminal to actually make the virtual robot move. So now you are doing the same thing as just now, and we can start to see the virtual robot to move in the simulation software. So now you moving forward
Mm-hmm.
like just now.
Yes.
So at the same time, we can see in this ROS software, you can see the path that the virtual robot is moving.
Mm-hmm.
And this laser scanning point, it actually show how far the laser is scanning, like the range. So the red color indicate the distance between the laser and the wall is quite near.
What about the green one in this regard?
The green, which means that there are more. I think the logic is reverse. I think the more range it will indicate in red color, the more far is like
Yeah, well,
the more green.
okay. All right.
Yeah,
Well, it's not exactly that, but I think you should must think of it as where it is red, that's the obstacles directly in front of the robot, right? If you think about it that way, I think it'll be a lot easier, right? So, given where
yeah.
it's going, those are the things that are bound, it is bound to collide in. But that's enough on that topic, so let's go on.
So now you keep moving forward until it near the wall,
Mm-hmm.
and then it will rotate. So actually in the script here, I have set the threshold. For the front is 0.3,
Mm-hmm.
but for the side is 0.424. So as you can see here, the front, checking the front scan is less than threshold or more than threshold. Is
Mm-hmm. How did you
the
pick that
front,
0.424 is your threshold?
I just square the 0.3 plus 0.3 square and then square root of the result. I get the 0.424. It's like r square equal to x square plus s plus y square. The trigonometry.
Why that distance specifically? Are you looking at the tangential distance and considering that to be like the furthest that you want to consider? What's going on there? Because I thought just looking in the front end, setting your front out distance or the threshold based on a particular value, 0.3 that we were given there was good enough. So why that computation before?
Because there are 5 range for scanning.
Mm-hmm.
The front is, for example, 0 degrees
Mm-hmm.
facing toward the left. The front left is like 45 degrees respect to the just now the axis.
Yes.
Maybe the right is positive, and then the left is negative 45,
Mm-hmm.
and then the left is like negative 90. The right is positive 90. So that's why I set for the front, right and left for different threshold, because in the like triangular, the front left 45 degrees is having the much higher distance in the triangle.
Yeah. So
that's why
that's why I'm asking, why did you have to pick that distance as the one that you set to be your threshold? Because it's not the index that is indicative of the obstacle that is directly in front of the robot. That is slightly to the side, right? It doesn't matter you go to the left or to the right, but that distance is not indicative of the things that are right in front of the robot. That is the zeroth index, if you say. So to me, I think that would just make your robot maybe slightly less predictable. It might work, but I'm trying to understand, why did you have to do that?
I'm doing that because I found that when I set the same threshold for the front left and right,
Mm-hmm.
the robot is too near to the wall. So that's why
Okay.
set a different range.
Okay. All right. I see. Yeah. Okay.
So
I will. Yeah. Okay. So it's a situation where normally 0.3 is supposed to work, because it's supposed to leave 0.3 right in front of it, and then even though the front left or front right might be slightly bigger, based on 0.3 you get enough space. But it's valid that you said when it gets to 0.3 it will be too close. So for now I can't take your word for it, but yeah, let's go.
Yeah, for the virtual it's actually too far, but actually when I run the real robot is actually too near.
Oh, it's okay.
So that's why I set a greater range for the front left and front right.
Okay. So this makes a lot more logical sense to me. If you say that you set this value based on the performance of the real robot, then it makes sense, because maybe you were encountering some lag. So by the time you set your parameter to 0, it will have moved a very significant distance to a point that is too close to the wall, right? So that is the reason I can accept. But for the simulation, I really find no reason for you to have done that. That's why the simulation is different from the real robot. But yeah, it's alright.
Yeah. So actually we have 8 conditions here. The first condition is check whether the front left, front free, front and the front right is whether it's free or not.
Yes.
So when it's 0 for 3 of the condition, it actually means that all 3 direction cannot be moved. So that's why we have to choose between left and right. So we will compare if the left 3 is 1. So at the here the left 3, we will check whether the left has much more range than the right. If it is yes, which means that is 1, we will turning left by 90 degrees. So we will set the angular velocity to 0.314. And for turning right, we will set to negative. And then we will sleep for 1.5 seconds. After 1.5 seconds, it will rotate by approximately 90 degrees, and then we will step back to 0.
All right. Thank you very much, Khai. Unfortunately, we are out of time, but thank you so much for the good presentation, and thank you for getting the time. All right. So you just hang on for me, and we'll wrap it up here. Okay. Alright everyone, this was Khai's presentation, and warm congratulations to him for getting the courage to come and present, and also for showcasing and giving the reasoning behind his implementation. And I'd like to encourage all those of you who would like to try this course or any other courses that we offer certification on to do so, and you can also come and showcase your work, and then you can get a certificate for it. So on that note, I encourage you to keep pushing your ROS learning.